In this hands-on activity, we do an experiment with things falling, and we try to explain why things falling together sometimes stay together, but sometimes move apart. Let's begin with a simple experiment with a pen and a notebook. Put the pen on top of the notebook and drop them together. Then reverse the pen under the notebook and drop them together again. Galileo stated that things with different masses but made of the same material fall with the same speed, if they fall freely and have no air resistance. In our first experiment, we saw that the pencil and the notebook did not fall with the same speed. When we drop the pen on top of the book, the notebook has an acceleration less than gravity because of the air resistance. The pen is slowed down to the same acceleration as the notebook because it's resting on top of it. When the pen is under the notebook, it is free to travel faster than the notebook, and thus it separates from the notebook. If the pencil is falling faster than the notebook, it is because the pencil is falling with acceleration approximately equal to the acceleration of gravity, g, while the notebook has less acceleration because of the air resistance. So we see that if things fall together, they must have the same acceleration, which is either g or less than g. Now we come to the main activity. We will need a ruler, some tape, and some coins. We are going to let the ruler and the coins fall, but we are going to fix one end of the ruler. We use the tape to fix one end of the ruler to a table. We hold the ruler horizontally and put the coins on the ruler. Then we let the ruler go and see what happens to the coins as the ruler falls. We have seen earlier that if things fall together, like some of the coins and the ruler, they must have an acceleration equal to g or less than g. But if they move apart, like the coins that separate from the ruler as they fall, they must have different accelerations. The reason is that the coins are falling according to Newton's second law of motion in a straight line, while the ruler is falling according to Newton's second law of rotational motion. From the equation for Newton's second law of motion in a straight line, F equals ma, we can find the linear acceleration of the coins. But from the equation for Newton's second law of rotational motion, tau equals I alpha, we can find the rotational acceleration, how fast the ruler rotates around the point where it joins the table. Now we can find out which part of the ruler moves with an acceleration greater than g, and that will tell us where the coins will come off. We calculated from a equals r alpha equals r tau over I. The moment of inertia for a bar like the ruler is 1/3 ml squared, where m is the mass of the ruler and L is its length. We see that A is greater than G when the distance from the hinge joining the ruler to the table, R, is greater than 2L over 3. So this is why only coins more than 2/3 of the length of the ruler away from the hinge will separate from it, because they can only fall at an acceleration g, while the ruler is falling with an acceleration greater than g. In this activity, we have introduced the difference between linear acceleration for the coins and angular or rotational acceleration for the ruler, and have seen how we can convert between them. Your students will enjoy doing the activity and will be surprised that something can fall under gravity with an acceleration greater than gravity.